2's complement representation is a way of representing both positive and negative numbers in binary. Let's take a look at an example of a positive number represented in 2's complement in order to begin understanding how this representation works. If we look at the number 001000, the way that we determine the value of this 2's complement number is as follows. Each bit represents a power of 2, with the rightmost bit representing 2 to the power 0. The next bit is 2 to the power 1, then 2 squared, 2 cubed, 2 to the 4th, and finally negative 2 to the 5th. Having the most significant bit represent a negative power of 2 rather than a positive power allows us to express both positive and negative numbers with our notation. If your number has a 0 in a certain position, then the power of 2 associated with that position is not present in your number. If the number has a 1, then that tells us that the corresponding power of 2 makes up part of the number's value. To figure out the value of the number 001000, we see that there is a single 1 which is in the 2 cubed position, so this number is equal to 2 cubed, which equals 8. Note that if I wanted to represent the same number 8 using a larger number of binary bits, I would simply add some leading zeros to my positive number. For example, the number 8 represented in 8 bits 2's complement is the same as the 6-bit representation, but with 2 additional leading zeros. Now, let's try a negative number. Negative numbers in 2's complement representation always have a 1 in their most significant bit. What is the value of 101100? We apply the same logic as before. Now we have a 1 in bit positions 2, 3, and 5. That means that this number is equal to negative 2 to the 5th plus 2 cubed plus 2 squared, which equals negative 32 plus 8 plus 4, which equals negative 20. In the case of negative numbers, if we wanted to represent the same value, negative 20, using more bits, one would simply need to append leading ones to the number to end up with the same value. For example, negative 20 using 8 bits is 11101100. Let's check that this is correct. This number is equal to negative 2 to the 7th plus 2 to the 6th plus 2 to the 5th plus 2 cubed plus 2 squared, which is equal to negative 128 plus 64 plus 32 plus 8 plus 4, which is negative 128 plus 108, and that is equal to negative 20. Let's take a look at the range of numbers that can be represented using n-bit 2's complement. Let's begin with our example of 6 bits. The largest positive number in that case is 0 followed by 5 ones, which is equal to 2 to the 0 plus 2 to the 1 plus 2 squared plus 2 cubed plus 2 to the 4th, which is equal to 1 plus 2 plus 4 plus 8 plus 16, which equals 31, which is also equal to 2 to the 5th minus 1. The most negative number using 6 bits is 1 followed by 5 zeros, which equals negative 2 to the 5th, with no positive component added to the number, and that is equal to negative 32. So in general, for n bits, the 2's complement number can range from negative 2 to the power n minus 1 through positive 2 to the power n minus 1 minus 1. An easy way of converting between positive and negative 2's complement numbers is by flipping all the bits and adding 1. For example, earlier we calculated that 101100 equals negative 20. If I take this number and flip all of the bits, I get 010011. I then add 1 to that, which results in 010100. This number is equal to 2 squared plus 2 to the 4th, which equals 4 plus 16, which equals 20. This tells us that our original number, 101100, was equal to negative 20. The same methodology can be applied in reverse. If you start with a positive number 20, which equals 010100, and you flip all the bits and add 1, you get 101011 plus 1, which equals 101100. This brings us back to our original number, which is minus 20. So to easily determine the value of a negative 2's complement number, one flips all the bits and adds 1 to find the corresponding positive number, say x, which in turn means that your original negative number had a value of minus x.